The idea of creating artificial creatures has obsessed us for millennia. But for the purposes of this exercise, before we go any further, I'm going to ask you to purge any of the following thoughts from your head. Checklist. Hephaestus, expelled from Olympus and then built 2 servant robots. The Bhutavanta Yanta, or spirit movement machines of 12th century India, made to protect the relics of Buddha. The chess-playing mechanical Turk, just a bloke in a box pulling levers. Mary Shelley's Frankenstein, he walks, he talks, not a lot else. Kubrick's Hal, don't call me Dave. C-3PO, R2-D2, K9, NS2, I mean, seriously, these are just numbers and letters. Robbie the Robot, Robot Lovers, RoboCop. Feeling better? Okay, let's get going. I'm Hannah Fry, I'm an Associate Professor in Mathematics and I am AI curious. And this is DeepMind, the podcast series where we look at the fast-moving story of artificial intelligence. We've been talking to the scientists, researchers and engineers based at DeepMind in London. And we're looking at how they're approaching the science of AI and some of the tricky decisions the whole field is wrestling with at the moment. So whether you just want to know more or want to be inspired on your own AI journey, then this is the place to be. You see, the thing is, robots sell. We've long lusted after the idea of upending the natural order with human ingenuity. We just can't seem to leave it alone. And in this episode, we are looking at AI and robotics. Murray Shanahan is a senior scientist at DeepMind. He's also a professor of cognitive robotics at Imperial College London. And growing up, Murray was utterly mesmerised by science fiction. So you can picture his face when the Hollywood film director Alex Garland approached him following the publication of his book, Embodiment and the Inner Life.
Alex contacted me and said, I'm writing a script for a film about AI and consciousness, and I read your book and it helped to crystallise some ideas, and would you like to chat about it? And so, of course, it was it was a great opportunity to get involved in a science fiction film, and then to my great good fortune, it turned out to be an absolute cracker.
And that is how Murray became scientific advisor on the Oscar-winning film Ex Machina. I met with Murray to get a potted history of AI. Murray, people tend to think of AI as this very new thing, a very modern invention, but it's actually been around for quite a long time.
It has. The idea of artificial intelligence, the idea of making artificial creatures dates back to Greek mythology. But the sort of modern conception of AI perhaps really dates back to Alan Turing's paper published in the 1950s, where he first kind of asked the question, could a machine think? And gave a number of kind of refutations for counter-arguments to the idea that a machine could think.
This is where the Turing test comes from.
This famous paper inaugurated the so-called Turing test. Of course, Turing didn't call it the Turing test, which is the idea that we should subject a machine to a test to see whether it's indistinguishable from a human in dialogue. The term artificial intelligence was actually coined by John McCarthy, a Stanford professor. He was at MIT at the time. And John McCarthy organised a conference in 1956, bringing together a lot of leading thinkers in maths to try and scope out the idea of building a thinking machine. And he coined the term artificial intelligence.
What did they describe it as at that time? How did they see artificial intelligence?
John McCarthy, in particular, his idea of artificial intelligence that he had in mind was a kind of system that would answer questions, really, and be able to engage in dialogue with humans.
Something you're actually just talking to.
So something that you're talking to, although, of course, in those days, it wouldn't have been through speech. It would have been by typing in at the keyboard. And it was very much a disembodied notion of artificial intelligence. So this system didn't have a body and interact with a physical world in the way that we do or animals do, or indeed that robots do. So they weren't really thinking about robotics at that point.
I'm sort of imagining something like HAL in 2001: A Space Odyssey, except typing in rather than speaking to.
And a kind of nice version. Their approach to artificial intelligence was to build systems that reasoned in logic. And we now think of that whole sort of approach to artificial intelligence of using logic and reasoning as so-called good old-fashioned artificial intelligence, or GoFi, or classical AI.
Now, I know I did a bad thing there. I mentioned how, but nobody ever said that this was going to be easy. But to recap, in classical AI, you have to write down a complete list of rules for how you want your agent to think. If this happens, then do this. If that happens, then do that. It's a nice idea in theory, but if your agent is going to know how to handle every possible scenario you can throw at it, it's going to need to be a long, long list.
There was a project called Psych, which attempted to write out all the rules of common sense to build an enormous encyclopedic database of common sense. So
can you remember any of them?
Well, I mean, there'll be things like if you've got a container and you put something in that container and then move that container somewhere else, then the thing that was in it gets moved as well.
Common sense.
Yeah, stuff like that, And if you buy something and pay for it, you'll have less money than you had in the first place. So do I think it's impossible to do that? I think it's impossible in practice, because it turns out that the sheer number of rules that you would have to write is absolutely enormous.
We might have moved away from these long lists of rules by now as a way to teach our artificial intelligence in favour of agents that can learn the rules for themselves. But the skills that we want our AI to have, like good old-fashioned common sense, are just as important now as they ever were. Imagine one day, long into the future, a wealthy computer scientist builds an AI to manage his stamp collection. He plugs it into the internet, gives it access to his bank account, and sets it the challenge to buy as many stamps as possible. At first, the agent acts as its creator intended, signing up to eBay, bidding on stamps. But after a while, it gets another idea. More money equals more stamps. So why not start trading on the stock market to make more money? And it soon realises it can get the stamps cheaper if it can get them at source. So the agent buys up a factory, converts its manufacturing process to stamp making, and goes on with achieving its goal. But of course, the limiting factor here is paper, more stamps. So it starts commanding forests to be felled, the wood to be processed, all to feed its single-minded ambition, more stamps. Now, there's no denying that the AI is doing what it was told, but it's doing so at any cost. And any agent without some kind of common sense will be at risk of taking our instructions a bit too literally. This might be a bit of an extreme example, but Victoria Krakovna, a research scientist at DeepMind working on AI safety, is already seeing agents that aren't exactly behaving in the way their designers intended.
A reinforcement learning agent that was playing a boat racing game. And the intended behavior there was to go around the racetrack and finish the race as soon as possible. And the agent was encouraged to do this by having these little green squares along the track that would give it rewards. And then what the agent figured out is that instead of actually playing the game, it could be going around in circles and hitting the same green squares over and over again to rack up more points. Then you have this whole situation with the boat going in circles and crashing into everything and catching on fire and still getting more points than it would otherwise get. These kind of situations are quite common.
But because you haven't ever stopped the AI from doing that or told the AI that you don't want it to do that, that's a perfectly sensible solution for it to come across.
Yeah, from the perspective of the AI, it can't really tell that this solution is a cheat. It's just something that gives it a lot of reward. So it can't necessarily distinguish between a degenerate solution and a really creative solution that humans just haven't foreseen.
There are plenty of examples like this. One team of researchers created an agent inside a very simple two-dimensional computer game and tasked it with building itself a body to get itself from the start line to the finish line. Quite quickly, it worked out that it could just build itself taller and taller and taller until it was as high as the track was long and then just flop forwards to cross the line. And there was the agent playing the game of Tetris, which realised it could just pause the game forever and never lose. But there is a balancing act here. We don't want our AI misbehaving, but we also don't want to restrict our agents too much.
And this is part of what's tricky about achieving safe behavior, is that we don't want to hamper the system's ability to come up with really interesting and innovative solutions that we have not foreseen. So we don't just want human imitation. We want superhuman capabilities, but without unsafe behavior.
There is a very fine line between a naughty algorithm and one that's finding innovative solutions to problems that humans haven't been able to solve. The AI doesn't know the difference between the two. It doesn't understand what's really important to us. It doesn't have any common sense. And that means you have to be very careful when you're setting up incentives and rewards for your agents.
Part of the reason that this is so difficult is this general effect that's called Goodhart's law in economics. What Goodhart's law says is that when a metric becomes a target, it ceases to be a good metric.
A classic example of Goodhart's law comes from British India, when authorities offered cash rewards for dead cobras as a way to decrease the population of snakes. Unbeknownst to the British, the locals started to breed cobras in order to take advantage of the reward. As soon as the authorities found this out, they scrapped the scheme altogether and revoked the rewards. But now there were these snake farms everywhere filled with worthless cobras. So what did the locals do? Release the cobras into the country, resulting in an increase in the cobra population. This is what the scientists call a specification problem, when your specified objective fails to bring about the intended behavior.
This is generally quite likely to happen because human preferences tend to be quite complex, and whenever we try to distill them into some kind of specification or something that we say we want, it's going to be a lot simpler than our real preferences are and wouldn't necessarily capture everything that's important to us.
Let us imagine we're living in the future where robot butlers are commonplace. You clearly specify the objective for your robot. It should serve you at all times. Now, how is that agent going to feel about its own off switch?
Your robot always has an incentive to preserve its own function. If it gets turned off, it can't vacuum the floors anymore, it can't bring you coffee. It would want to disable its off switch, for example.
Jan Leiker is a senior research scientist at DeepMind, also working on AI safety.
If you turn it off, then it can't vacuum the floors. Yeah. So if it understands how the off switch mechanism works, it would want to disable it. What we want is our systems to actually do something that is good for us, right? To do something that we actually wanted, and not just what we said we wanted.
But how do you get around these kinds of problems? Well, we already know that writing a long list of do's and don'ts won't work. However long your list gets, you're always going to forget something. The new breed of learning agents is going to need a different approach.
So one direction that we are pursuing is learning reward functions for reinforcement learning agents. And you can kind of think of this as learning what your system should be doing from human feedback. So, for example, in one work that we did together with OpenAI is where we trained a simulated robot to do a backflip. And the way this works is like the robot does some movement, and then you watch a video of that movement, and you, or let's say 2 videos, and then you can compare which of those looks more like a backflip.
Jan's experiment has a human sitting and watching a screen, looking at an AI attempting to do a backflip. Each time, the human will feed back on whether the attempt was good enough, slowly nudging the agent in the right direction. Here is the key idea. With constant human feedback, the human can communicate their preferences without having to actually specify them and risk oversimplifying things in the process.
And after like a few hundred rounds of feedback, the robot can actually perform a backflip. It's kind of learn what the objective should be, that the objective should be a backflip and what a backflip is. This is difficult to specify precisely what a backflip would be, right? So in my case, like I can't do a backflip, right? But I can see if the system is doing a backflip. So in some ways, like this allows us to get superhuman capability.
The AI then is essentially being rewarded by pleasing the human in a way.
Exactly. All right, so we can do a little experiment.
Okay.
I'll try to teach you to make a sound
Okay.
by giving feedback. So you'll make 2 sounds, and then I'll tell you which of the sounds is closer to what I have in mind.
Okay.
Yeah, does that sound good?
Yeah, let's do it. So I'm being the AI here.
Yeah, you're being the AI, and I'm being the human teacher.
And you're training me essentially with reinforcement learning, and my reward function is getting you to be happy.
That's like, so the reward function here is like something that is in my mind, right?
Okay.
And I'm trying to teach you. So you can't directly see the reward. You can only see like my feedback.
But my objective is to get you to say you like what the sound that I'm making.
Exactly.
Okay, let's think of 2 sounds. Let's go for meep and meep.
First one.
Okay. Have you actually got something in your mind, or are you just making...
This went on for a while.
Beep, 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 and beep, duh.
But with Jan's feedback, we got
Beep and beep.
I'll go with the first one.
absolutely nowhere.
This is really hard because of the expiration problem, actually.
I mean, ultimately, if I was an actual AI, I'd have gone through 10,000 iterations by now.
Well, you have to have a human in the loop that reviews all of that, so it is kind of slow.
This is true.
But this is actually a problem that we have in our systems, is that, like, in order to give useful feedback, you have to have useful examples, right? In this case, you produced sounds that are very similar, and like the sound I had in mind was like very
Totally
different. So I don't really like have the opportunity to give you very useful feedback, right?
Damn, my optimization strategy was terrible here. Okay.
But this is like, basically, this is the same thing would come up with a backflip, right? Like if your robot just like lies on the floor in like 2 different ways, like what are you going to do?
But you would hope, though, after I'd had maybe 100 goes at it, I'd end up with something that began to approach what you had in mind.
Yeah, definitely.
Is it like... Oh, no, I'm not allowed to ask any questions, am I? Because I'm an AI.
I mean, ideally, this is at some point, this is what we'd want our systems to be able to do, right? I would just like describe the sound to you in natural language, and then you could just do it. That would be really cool, right?
Yeah.
So this is the kind of research that we want to do in the future, or that's like the kind of systems that we want to figure out how to build.
Oh, okay. Actually, everything I've done so far has been like voices. You didn't say that it had to be a vocal thing, did you?
Yeah.
Okay, hang on. All right, how about this? And...
The first one.
Ooh!
The first one was actually what I had in mind. Yeah, this is great.
So far away.
The only problem with setting up reinforcement learning with a human standing over it, offering feedback at every stage, is that it is monumentally slow. Now it would take an agent months, if not years, to master a game like Atari. And even then, you'd need to hire a pretty large group of poor students to do the boring job of supplying feedback in real time. But there is an alternative. You can rustle up a slightly more sophisticated learning partnership.
So what we do when we actually build these systems is we don't literally do the experiment that we did now. And instead, we train a neural network, a second neural network, that learns how I would give feedback as the human. And then the neural network can teach you because it can just oversee all of the things you're doing.
By now, neural networks have become really good at spotting patterns. Dog, not dog, backflip, not backflip. Perhaps you don't always need a human in the loop laboriously giving feedback. Why not have 2 agents, one attempting the task and the other deciding if it succeeded?
The reason why this works very well is because evaluating the objective is an easier task than producing the behavior that achieves it. So you can have, like, for example, in the backflipping robot, all the neural network has to do is like look at what the robot is doing and see whether it's a backflip.
You're listening to DeepMind, the podcast, a window on AI research. But of course, where this stuff really comes alive is where you take the ideas, take them out of a computer simulation, and allow your imagination to roam into the world of embodied AI. Robots that learn how to cook, robots that learn how to pack fruit in crates, tuck you into bed, and perform backflips. It's time to visit the DeepMind Robotics Laboratory.
We are standing right outside of the DeepMind robotics lab.
This is your lab. This is where you spend your days.
Well, it's not just my lab, but yes, it is our lab.
Can we go inside?
Yes, we got our badge.
This is Jackie Kay, a software engineer.
Packed to the rafters with robots. It's very
Yes.
cool.
We're basically running out of space.
It's quite noisy in here.
Yeah, we got a lot going on today.
This place isn't quite the high-security basement laboratory you'd imagine. There are half-assembled robot arms and machine parts scattered all around the place. Some look like mechanical hands, others quite a lot like red KitchenAid-style food mixers. And curiously, there is a SpongeBob SquarePants mascot hanging from the ceiling.
Hey kid, check it out!
I think we use it as kind of a punishment if somebody leaves a tool lying around, and when they're supposed to put it back, we'll throw SpongeBob in his face or something.
That seems like a fair punishment.
Much of the work in this room focuses on getting robotic arms to learn how to do simple tasks. Each robot is bolted to the floor in its own cordoned-off area, and as we come in the door, there's one that's caught my eye.
You know that game that you play when you're a kid, and you have a tennis bat and a ball attached to it, and then you can kind of play tennis on your own? It sort of looks like a robotic version of that.
It's called the ball in a cup.
Oh, so it actually
Yes.
is.
It is exactly that. It is trying to swing the ball into that little basket. So you can see it swinging the ball around a little. It's actually tracking the position of the yellow ball, and it's trying to minimize the distance from that ball to the area inside the basket.
It did it!
Got it! Yes!
Not exactly a smooth delivery of the ball into the cup, more a slightly clumsy, lucky flip. Of course, if your ultimate goal was to make a perfect cup and ball playing robot, you could directly program a machine to do that without fail. You can build robots that perform simple tasks in much more elegant ways. But that's not really the point. Here's Raya Hadsell, Senior Research Scientist at DeepMind.
A robot is a machine that can take over a task. One can say in the broadest sense that your dishwasher at home and your vacuum cleaner are both robots. Because they do something complex, they run on their own, they have some autonomy to them. Of course, we also like to think about robots as having some intelligence. And then you get more into the realm of a robot with AI. And I'm particularly interested in saying, how can we take this AI technology and make it work on robots so that we have embodied AI?
And that is an important distinction. The focus of the research in this robotics lab isn't to create robots that are told what to do, but to have them learn their own skills, much in the same way that other agents do here. The robots here are what's known as embodied AI.
So let's say, the task is a robot that's trying to lift a box. I, as the programmer, in a kind of traditional setting, would say, go to box, open hand, move hand, 30 centimeters towards the box, close hand.
But this is different.
Yeah, this is sort of taking what we want and then figuring out how to accomplish what we want.
Every few seconds, this particular robot will have an attempt at getting the ball into the cup before pausing, resetting, and having another go. And every now and then, by chance, the ball lands in the cup and the robot is rewarded with a positive score, just like if it was playing a computer game.
The reset in between the training episodes, where it untangles itself or flips the ball out of the cup, those are scripted. But then when it actually tries to accomplish the task, that is a policy which it has taught itself through experience.
Over time, from everything it learns and the scores it receives, the robot builds a picture of how the ball moves and how this relates to the robot's own movement.
So had we come in right at the very beginning then, what would we see?
Just completely random noise, probably very chaotic, swinging around.
It did it in one.
That was
It did it in one.
That was, wow. That was in 3 seconds.
So will it know now that that movement gave it a successful result?
Yes.
And so the next time that we see this, do we expect it to be better than when we walked in?
Yeah. It will try similar actions that gave it a positive reward or a success.
It's just sort of sitting there quite smugly right now.
Yes.
There is a big advantage to getting the AI to figure out tasks for itself. You'll end up with a robot that is much more flexible out of the box. It doesn't matter what you want it to do. Tie a knot, stack some bricks, peel a banana. Just as long as you can clearly communicate your objective, you don't need to specify a long list of instructions for these robots. And perhaps they'll come up with a new way of banana peeling that you hadn't thought of. But there's also a big drawback in training AI that has a physical body. They are much slower to learn than all of the disembodied agents you'll find in this building, the ones that only exist inside a computer.
Other researchers are able to take advantage of parallelism. That is, they run their environments in simulation on computers. And they can run them in parallel on hundreds of different computers. We're all gathering data about this environment they're trying to learn something about. We only have, there's 4 robots here, and they're frequently not running the same experiment, so it might just be one robot collecting data. And that means our training will be orders of magnitude slower for comparable tasks compared to ones that are run in simulation on computers.
Progress is slower in this room, and you can tell. The agents here are a little less accomplished. In another corner, another robot is trying to pick up a Lego brick with a hooked gripping device, kind of like a claw. And there's a rather ominous box of mangled Lego bricks next to it.
In the exploration phases of training, it will sort of randomly open and close its gripper, and I think this one has some shaping to close its gripper when it detects it's close to the brick.
Oh, close now. Close.
And then it also has a fixed training time, so after some number of seconds, it will just give up and go back to the start and then try again. Lego is sort of this building block to general purpose manipulation. If we can stack like 2 bricks together, we can then do kind of arbitrarily.
It's gonna break it.
Oh, it's fine.
Sorry, I got distracted by the robot smashing up the Lego.
There is real potential here. And so Jackie and the team are constantly trying to find ways of speeding up that learning process.
One technique that we are looking into and that some researchers here have done really cool work on in the past is something we call sim to real, or simulation to reality transfer, which is where you take a simulation on a computer that models your robot, and we can learn kind of in broad strokes what the robot is like, how its actions affect its environment, and how it can do something similar to a task it's trying to learn in real life. So once we figure out all of that in simulation without even touching the real robot, we can transfer the data it's collected onto real hardware.
So you can cheat, basically.
Yeah.
You can cheat by imagining the real robot within a computer, calculating all the physics that would happen in real life, and then use the same techniques. Use that army of computers to give you a bit of a head start before you even apply it to the real physical robot.
Exactly.
So the real robots end up acting the same way as your simulated robots do?
Well, they start out acting the same way as their simulated robots do. And then as they train more, they might start behaving slightly differently or better when they go into reality.
Using simulation might give you a head start on reality, but it's never going to match precisely. The real robot has to contend with grip, friction, gravity, wear and tear, all of which play important roles in the real world, but none of which will be perfectly represented inside the computer. And all of that means, well, I think science fiction may have set some false expectations.
One thing that I am a little bit surprised about being in here, don't take this wrong way, but these robots are a bit rubbish.
Yes, it's true. I mean, we've got a lot of work to do.
But as with so much of what happens here at DeepMind, It's not so much about these exact agents. It's not about cup and ball or Lego stacking. It's about the type of intelligence being acquired and how that fits into the bigger picture.
We want to demonstrate general purpose physical intelligence.
Physical intelligence.
Right. So contrasting that with kind of a intelligence that's not embodied, which maybe can learn to play games or maybe even understand language. Physical intelligence is looking at how the physical actions of your body affect the real world. So we want to take a wide variety of tasks, playing with objects, using tools, maybe walking around or running in the future. And we want to show that robots can teach themselves those how to do those tasks.
In the physical world?
In the physical world, yes.
But physical intelligence is, of course, only one type of intelligence, one string to the robot's bow. And DeepMind, as we've seen, dares to dream big. Here's Murray Shanahan with the big finish.
The holy grail of AI research is to build artificial general intelligence. So to build AI that is as good at doing an enormous variety of tasks as we humans are. So we are not specialists in that kind of way. A young adult human can learn to do a huge number of things. You can learn to make food, you can learn to make a company, you can learn to build things, to fix things, you can do so many things, to have conversations, to rear children, so all of those things. And we really want to be able to build AI that has the same level of generality as that.
If you want to know more about robotics and technical AI safety, then head over to the show notes where you can also explore the world of AI research beyond DeepMind. And we'd welcome your feedback or your questions on any aspects of artificial intelligence that we're covering in this series. So if you want to join in the discussion or point us to stories or resources that you think other listeners would find helpful, then please let us know. You can message us on Twitter or you can email us podcast@deepmind.com.
Good stuff.